thank you, Paolo, for the intro, for the invitation, for being here. So I think the overlap between all the subjects that just Paolo listed and what I'm going to talk about is, vaguely speaking, complexity science. So I would not be talking about applications that are closer, I guess, to the usual seminar series you have here. But I hope that some of the things that we talk about can be translated maybe to other domains relatively easily. So as you can see, I'm going to focus, and this is what I have been doing for the last 5 years, about social systems. So, okay, we all use networks, okay, to encode interactions, and the social systems is a standard playground for this kind of approaches. And the typical approach is to encode the basic building blocks, which are interactions, for example, between humans into a network, and humans can interact. So the social fabric of interaction can be not only represented by dyadic links, but we can also think processes that happen at the level of groups. So in general, whenever you observe a system and commit to a given representation, there are some assumptions that are basically the building blocks of your theory. So if you assume that units are connected through pairwise links, you go with graphs, which are super powerful. However, if you want to have the building blocks that already encode the possibility of many body interactions as opposed to dyadic interactions only, you may want to move into what has been probably a bit naively called higher order approaches. I'm saying naively because many things can fall under the umbrella of higher order. Could be layers of a multiplex, could be dependencies like paths, second order dependencies on a graph. So in this case, what I mean for a higher order is order larger than 1, with 1 being the interaction order between 2 units. So this is what I mean for order. Basically, how many units you have that interact at the same time. So when you do this, what you see is that if you start from a data set of interactions, for example, A, B, C, so basically a set of sets, if you project this into dyadic couplings only, you have standard links, and then you glue them together and they form a graph. But if you keep the full representation of who's interacting with whom, so you might have many body interactions already in your data set, then you're better off using a representation that doesn't lose this kind of complexity. So for example, simplicial complexes or hypergraphs are the structure that you might want to use. There's a tiny difference between the two of them, which is that in simplicial complexes, whenever you have an interaction in the complex, you also need to have all the sub-interactions contained. In this talk, I will not go into the details of the difference between these two. I will call them, in general, higher order interaction, and I will refer to simplices or hyperedges interchangeably as an interaction that happens at the level of a group. Now, this is clearly not new. There's a lot of mathematics that comes before and after this consideration. So it borrows from algebraic topology and combinatorics, and has found many interesting applications in the last 15 years, I would say, in a variety of domains. In my case, again, I want to focus on what are the implications of this approach when it comes to modeling processes that happen at the social level, so the level of social groups of individuals. So we'll start with an example from adoption dynamics, which has been widely used in network science since 25 years and more. So we talk about adoption dynamics whenever you have something that spreads on top of a social network of interactions between individuals. So it might be norms, might be rumors, might be behaviors in general. So for example, a behavior of spreading like the one of smoking habits. This could be good or bad things they may want to prevent or force the adoption process. Now, traditionally, whenever you study spreading processes on networks, you start from the same paradigm used for spreading of infectious diseases. For example, simple contagion, which assumes that whenever you have a pair of nodes interacting, one of which is susceptible and one of which is infectious, or non-adopter and adopter, if you talk about behavior, for example, then the transmission can happen with a given probability of infection per active link. An active link is simply a link between an S and an I node. Now, when it comes to processes that happen at the social level instead, so not infectious diseases, but like behaviors, there is a enormous body of literature that shows that there are more complex mechanisms of peer pressure and social influence that are in place. And this led to the development of different models that follow, let's say, within the domain of complex contagion models that basically assume that the sources of infections for a susceptible node to switch their behavior are not independent from one another. So you can think of the standard threshold model by Watts, in which you need a fraction of your neighbors to have adopted a new technology, for example, before switching yourself. Now, the assumption here is that you need multiple sources, but these still happen at the level of pairwise links. So what we might want to do is to elevate this at the level of groups instead, so that there are simultaneous sources of infection. So infection pressure can come from the group itself, not only from dyadic links. So let's say I'm at the bar, I want to drink a beer, the table starts ordering a bottle of wine, I might just switch for the wine. And this is something that happens collectively at the level, again, of the group. So it cannot be factorizing to a collection of infection pressures at the level of links. Now, the simplest model we can do to adopt this higher order representation is basically to extend the SI or SIS model to account for group interaction. So what you can do, you can keep the idea that a single link can infect you. So if this is infected and this is susceptible, the red node can pass the infection with a given probability per contact, and this is beta. But if you're part of a group of which all the other nodes by yourself are infectious, then the group itself puts some additional pressure, social pressure on you to adopt a given behavior. And you can represent this with a different parameter that we call beta triangle. Obviously, you can generalize this up to any dimension. For simplicity, let's stop now at dimension 2, so at the level of links, and 2 simplices, which are this triangle here. Now, formally, you have all these channels, possible channels of infections, and then you have the standard probability of recovering. So you can go from S to I and back to S. Let's say you don't have immunity in your system. Then you have 2 standard control parameters, which are the infectivity at the level of links and triangles, broadly speaking. Then you can normalize them if we're going now for a mean field approach, for example, using the average degree as per the standard epidemic models. And then what you track is the standard macroscopic order parameter given by the density of infected individuals in your system. So you can write down the mean field equation as a standard SIS model, so you can track the density of infected nodes at a given time. So you subtract the loss of infectious node due to the recovery. Then this is the standard SIS, so you have susceptible nodes, which locally are proportional to the susceptible nodes in the entire population, and each susceptible node is in contact on average with K infectious nodes, which is rho. And then for each link, you have a given probability of infections, which is beta. And then you can add the contribution coming from the groups. So here you have a susceptible node, again, that is part on average of K triangle groups, and the other 2 nodes need to be infected, so you have the rho squared. And the group passes the infection to you with this probability beta triangle. So we just extended the standard SIS now. You can define this up to any dimension. If you're interested, I can give you some ideas of what happens in this case. But if you stop here, you have a simple quadratic equation that you can solve. You impose that rho needs to be in the acceptable range of 0, 1. And so you have up to 3 solutions, one of which is the absorbing epidemic-free states. So at the end, you have no infectious nodes in your system, and then you have other 2 acceptable solutions. Now, if you study this is a standard phase space for the SIS. So I'm plotting the density of infected nodes against the link infectivity, so the infectivity at the level of the pairwise interactions. And here I'm changing the level of the infectivity of the groups. So when you have the darkest color is the standard SIS transition. It's a continuous transition at the critical threshold of lambda 1, since we are scaled for the degree. So if you increase the contributions coming from the group, you have just a higher density of infected individuals in the endemic state. So the epidemic is sustained, then you have a higher density. If you increase this even more, however, we have a change in the nature of the transition. So not only the threshold moves back, but what you see is that what was a continuous phase transition becomes an abrupt transition. So it's discontinuous. Now, what this means is that if you study the phase space and look at the equations, you have at the level of the dynamical system an unstable branch that splits your phase space into two basins of attraction. So if you start below here, so you start in this region of the phase space, you end up in the stable absorbing epidemic free state. If you start above, you end up in the stable state here when the epidemic is sustained. So you can think of this as a critical mass effect, effectively. So if you have a system in which you seed the infectious nodes and the seed is lower than what is given for a given level of infectivity by the unstable branch, so if you start in this example below here, these are stochastic simulations, and these are the prediction from the simple mean field. You see that the epidemic doesn't take place, otherwise it reaches the stationary state. So just by introducing this peer pressure from the group, we recovered a critical mass effect that in a network setting, you need to kind of put a way more complex infection dynamics into your system. Instead, if you change a bit the representation of the structure, this comes quite naturally. And this is nice because it doesn't happen only for SIS type of processes. So if you study different dynamical processes on these higher order structures, there's kind of an idea of a general pathway towards explosive phenomena when you observe this change in the nature of the transition from second order to first order. If you go higher with the dimensions, now this might be not visible from here, but basically you also account for four-body interaction, so on and so forth. In the endemic level, you have, as you expect, a higher density of infected nodes, just with contributions that are smaller for each order interaction. But close to the epidemic threshold, then you start having multi-stability effects. So in this case, you have one stable state, which is zero, but then you have two non-zero stable states. So here we might say this is not, it's not proven, but seems to be that the more order of infections you consider, the more stable states you might have, the more non-zero stable states you might have in your system. And notice that this multi-stability also, appears even for completely connected structures. So it's something that comes directly from the model definition, not from pathological configurations of how your nodes are connected. So before, they found multi-stability on hypergraphs contagion by basically creating well-connected structure with orders of high, with big, let's say, groups connected, very connected within each other and loosely connected among them, let's say community structure of hyperarches. And they were getting this kind of multi-stability behavior here, but you can also recover it on complete structure. So this also means that it's something that the model accounts for independently on what's behind the spreading process. This has also been found in many other dynamical processes, as I said. One other nice example, I haven't worked on this, but this is extremely interesting, is the case of synchronization dynamics. You might have used, for example, the Kuramoto model when you have phase oscillators that try to synchronize their oscillatory patterns. So each oscillator has a proper frequency and then tries to synchronize and adapt their phase according to the connectivity in a given graph. And traditionally you have, if you track the coherence of your system, so how much aligned these oscillators are, you have a continuous rate transition from a non-coherent to a coherent state. If you add, as before, high order interaction, so in this case you have a tensor of connectivity between three nodes, you see what we saw for a spreading process. So you move from, well, this is just the case of the three-body interaction, but you also have bistability in here as well. So abrupt transitions also appear at the level of synchronization patterns. In addition, the interesting thing about synchronization problems is that you might have negative couplings between links. So two links that do not try to align their faces. So locally, you actually try to diverge, but then the groups manage to keep the system together and to reach synchronization. So in this case, you have just negative couplings at the level of the links, and the groups are tuned down. And Here I'm plotting with different colors the different phases of the system of interacting oscillators, and they are all basically rotating with a different phase. Then as you start increasing the group interactions while keeping the negative coupling in place for the links, you may reach situations like this one if you have patches which are locally synchronized. Now, why is this interesting at all? Because there are many processes that interact with each other, so studying group behavior may be the driving force behind something that triggers behavioral response at another level. So for example, if you're interested in the spreading of infectious diseases, where you typically have continuous phase transition, if your system can be modeled as well at the level of behavior, so let's say adopting risky behavior or sticking to non-pharmaceutical interventions, then if you have a given change in the transition at the level of the behavioral part, then this might also translate to have an impact at the other level. So more in general, studying this kind of process at the level of groups might call for a better integration of behavioral aspects within, for example, models of epidemic spreading, but it's not only limited to this. Another example of why these things might be relevant is the case of critical mass dynamics. So whenever you try to study a system from the point of view of the critical size of a seed to start an infection or spreading of something, you're very close to the idea of critical mass theory well studied in sociology when you say that you want to trigger a major takeover of a system starting from a minority of committed individual that might be thought as the seed of your system of infectious individual, for example. And in the literature, if you look at what is the minimum size of this seed to take over the entire system, you have very different levels of critical mass that spans from 0.3% to 40%. So this was not very clear in the literature what would be the value of this critical mass. Turns out that if you use if you standard game used for these cases, which is the naming game, to account for group interactions, the level of critical mass can go down up to, in this case, this is an example, one single individual that was committed to a given norm and manages to take over the entire population. If you study this analytically, what you see is that there is an interplay between the fraction of committed individuals in your system and the level of social influence, so that here I'm plotting the density of the opinion of the minority. So it basically, when it goes up to 1, it's not anymore a minority, it becomes a majority. But then if you account for group interactions and you decrease the level of the fraction of committed individual, there's always a region here in the level of social influence that can actually sustain the opinion of the minority. So what it's basically telling you is that as soon as you can tune the social influence of your system, which is not something obviously we can do, but there is a range of, in this phase space where accounting for group interactions allows a vanishing size of committed minorities. So this kind of helps us understand why there are so many different values of critical mass that have been found across different studies. They were experimental studies, empirical studies from data, or people playing in games in a lab, or theoretical studies with models. So this kind of puts together within one single framework the different values that were found. You can also extend this beyond the two processes I described. If you're interested, there are many papers. Here I just stopped at 2022, but lately many more came out. So if you're interested in voter models, both continuous and discrete, majority root models, basically every consensus dynamics or opinion dynamics model you can think of have been more or less extended to account for many-body interactions, and there are some cool results there. This kind of shows how much people have been adding to this trend of going towards non-pairwise interactions for dynamical systems on hypernetworks. What I'm going to show you now is how we extended the model I presented before to account for more heterogeneity in the system. So the model I described before was like this. We limited ourselves to the case of links and triangles. This is obviously a big limitation. And we also, at the level of the dynamics, we said that a group would be infectious if all the other nodes were infectious. And this was another limitation again. Now, one way to fix this would be either to adopt threshold dynamics at the level of groups. This has been studied a lot. Or to basically avoid having one single parameter per order of interactions and to put everything together into a more flexible model. And this is what I'm going to briefly present to you. So you might have an infection pressure, which is proportional to the infectious nodes within your group, as opposed to having a fixed number of members of the group infectious in order for the group to be infectious. How to do this? Well, we took an infection kernel like this one, so you can think that the susceptible node part of a group of size n, of which I nodes are infected, may feel an infection pressure of this form here, in which you have an exponent that kind of lets you tune the amount of social influence perceived by the member of the group. So that if it's above 1, you have this superlinear infection pressure. You can also consider sublinear infection pressure, so you try to stay away from the opinion of the group. And if you put ni equal to 1, you recover the standard SIS dynamics. Now, we treated this using an approximate master equation framework that it's way more flexible than the mean field approach I described before. This allows you to play with the two quantities in place here, which are the two sides of the bipartite network you can use to represent the hypergraphs. So in the graphs, you can tune, you can think of the degree of the nodes. When you have groups, you have these two sides. You can have two distributions here, which are the size distribution of groups and the hyperdegree distribution. So to how many groups a single node belongs to. Now, in the approximate master equation framework, you have these two quantities, so you can consider ensembles of models that consider these two fixed distributions. Then you can track in time one structural parameters, which is the fraction of nodes with a given membership, so how many groups they belong to. And then you have also a dynamical quantity, which is you track in time what is the fraction of groups of a given size that have a given fraction of infectious nodes within. So with these two quantities, then you can actually study many more things than the ones we saw before. So for example, if you plug in one hyperdegree distribution and one group size distribution, you can see that simulations match with the analytical framework. This is somehow expected, but it's nice to check. And then you can also see that structure and dynamics can lead to the same behavior. So in this case, what I'm doing on the left, this is a plot like the one before. So I keep the structure fixed, hyperedges of degree 3 and all group size 4. And I'm increasing the level of social pressure, which was the exponent in our infection kernel. So this was exactly like what we saw before. However, if you actually keep a fixed superlinear exponent in there, we can recreate the exact same picture. So the phase space in which you have the higher endemic state and then the abrupt transition by changing the actual structure. So this kind of allows you more freedom to study the interplay between structure and dynamics. Also shows you an interesting phenomenon that was found in other models as well, which is the one of mesoscopic localization. That means that there is a given point in time where most of the infectious nodes in your system are confined in a single portions of the graph. In this case, they are confined to the largest groups. So the largest groups actually help to keep the epidemics alive. And you can study this with a minimal example in which you have a system of regular interactions of size 4 plus one single big interactions of size 15. So before you would have, in the regular case, this continuous transition, and if you add just one hyperedge of size 15 to your system, it becomes a continuous transition. So actually, one big group can actually self-sustain the epidemics. It's enough to keep the epidemics alive. Now, the next standard thing to think about, so we saw a bit the interplay between structure and dynamics. And the critical size of a seed of infectious nodes is to think about what is the optimal seeding, for example, to maximize or minimize if we want, if you change the perspective, the spreading process. So again, I'm going back to this idea that you can map a hypergraph into a bipartite network. This is a crucial, it's a useful point of view because it allows you really to see the connection between the two quantities that we have, groups and nodes. So traditionally, in pairwise graphs, the standard approach is to consider the degree as a powerful way of controlling what is the spreading power of a node. In this case, you have also groups. So you might be wondering, is it better to target nodes with a high degree or nodes that are part of big groups? So with the approximate master equation framework, we targeted this problem here. I'm not going through the exact details, but what you can see here is that I'm plotting as a function of the nonlinearity of the process on the x-axis and the seed size on the y-axis. If at the end the faster adoption was due to basically if you're better off with groups or with nodes. So we studied an optimization problem was the faster takeover. So if you have a red outcome, you were better off targeting nodes part of big groups. If you have a blue, you are better off targeting nodes which belong to a lot of groups. And as you see, there's no single answer here. So the answer lies in both the combination of how much your process is nonlinear, so what is the social pressure, the functional form of the social pressure in your system, and also where are the configurations of the groups. So here I'm changing from heterogeneous and homogeneous structures in the hyperdegree distributions and the group size distributions, and I just see the line that separates the two optimal portions of the phase space bends from one side to the other according to the interplay between these quantities here. Now, the last thing that we might do is to combine the two concepts together. So we were wondering, are there nodes belonging to big groups or nodes belonging to a lot of groups? Which one would be the best choices? We can actually put the two notions together. So to do this, we extended the standard notion of k-cores for graphs to the case of, we call them hypercores. So you can track for each node to how many groups the node belongs to and what is their size. So you can actually count and you can then create a decomposition of the graph in which you say a km hypercore is the induced hypergraph composed by nodes that have at least k groups of size at least m. So you start having this kind of onion-like decomposition of your hypergraph. So you can go up and down with the number of groups, of the size of the groups. And you see there, obviously, these things are nested. So one, if you go in one direction, the other one is contained within the other. And the nice thing is that once you define these hypercores, you can very easily define a hierarchy of nodes belonging to the hypercores. So we define this measure of hypercoreness that basically contains both the information of where are the nodes connected to a lot of groups and where are the groups which have the biggest size. So how high hypercoreness values tells you that a node is highly connected to a lot of groups of big size. As you see here, I'm just plotting the color according to the hypercoordinate set. It doesn't really remind the standard notion of betweenness or closeness centrality. So it's something that it's independent from what you would get from a standard force atlas algorithm for pairwise projection of this hypergraph. Now, if you use this hypercoordinates measure to seed a process, you can actually see that it works. Otherwise, I would not be showing this probably. Basically, the SIS process manages to have, here I'm plotting the average state spent in the endemic state by the nodes. So you can actually see that the hypercores manages to keep the epidemics alive. So it's more localized when you see them using the hypercoordinate centrality. Instead, for SI aerodynamics, so if you allow nodes to become immune after they got an infection, you have a way easier quantity to control, which is the final epidemic size. So what is the maximum number of nodes that got infected at any point in time during an epidemics. And you see that targeting nodes based on hypercores actually manages to increase the total outbreak size. Now for the last part, I would like to change a bit the point of view. So far, I hope I give you an idea more or less of what happens when you account for group interactions for dynamical systems that take place on top of a higher order population. So the population that interacts through higher order interactions, and this brings some interesting phenomenological consequences. In general, we can say that we can start from observations that reality happens beyond pairwise interactions. We formulated some models. We need some data to actually don't start from networks that are already projected at the level of pairwise interactions. And then we developed some methods to track this new representation of problems that arise. The next step would be to perform some in-lab experiments, for example. This is something that we keep thinking of and hopefully we'll do soon. But in general, what I would like to present to you is the idea that we can also look within these systems at what is the dynamics that is forming this group structure. So what are the microscopic dynamics within the system as opposed to the macroscopic phenomena that emerge when you put dynamical processes on top of these systems. So to do this, we gathered empirical data on social interactions, but these not to be already projected in graphs. So they need to be longitudinal in time and with a granularity that allows you to actually track group interactions with a fine scale. So we got these two data sets. The first one is Bluetooth connections. You might have heard this one is a Copenhagen network studies with freshman students in Denmark were given smartphones. And so these are all open data, you can play with them. So basically you have roughly 700 students tracked for 4 weeks, and you have a very granular signal strength, which is a proxy for proximity. And then the other one is a completely different study with different technology, which are radio frequency identifier placed on chest on kids in a preschool. So we're talking about university students and pupils of a preschool. And again, you have this longitudinal aspect of the system. So you can track for different contexts, so weekend, not weekends, playground, during class, and for different ages, what is the size of the groups. And you see, as we saw for the system, this is heterogeneous and depends obviously on the context of interaction. So you can think in class, obviously there are way more constraints than if you're playing in a courtyard, or if you're going out with your friends during the weekend. So this will shape obviously the size distribution, the group size distribution, but they're all heterogeneous. And then we can try to have a look at how people move between these heterogeneous sizes. So how do groups form and evolve, and how people navigate between the different groups. So the first thing we can look at is what we call node transition matrix. So you have a node that undergo a transition, so a change of group size, and then you see what is given a group size at the beginning of the transition, what is the group size at the end. So it's a conditional probability of moving from group size k to a group size k prime. You can do this for all the data sets, and what we found was that actually they do not look so different. So despite the age and the context of interaction, so some were really forced in class, some were free to interact in the courtyard playing, or the weekends for freshman students, they more or less present the same pattern. When you have, for small group sizes, that the most probable transition is towards a group of the same size, and then slowly you go into larger groups up to a cutoff point that depends on the particular case. If you then look at for how long these groups survive, you find broad shapes independently on the context and on the size, with obviously broader shapes for small group sizes. And this reminds to the concept of burstiness in temporal networks. So you can actually track this and see what is the interevent times between the appearance of groups of same size. And again, this is broad, calling for Burness effects in group interactions as well. The last thing we can actually look at is how does this group form and evolve. So the example I usually give is the one of droplets that fall down of a window of a train, let's say. You might see these droplets coming down, and then at some point they merge due to the surface tension that pulls them together. So in case of groups, is it the same? Do you have medium-sized groups that join the forces into a big one, or is it like a gradual process? You can study this. It's a bit hard because you cannot have the notion of who retains the group label as two groups merge. So we did was to look just at the biggest subgroups abandoning a group or the biggest subgroups joining a given group. So if you have a group of size 2, you can see in the disaggregation dynamics what is the biggest subgroup size coming out of this. Obviously it's 1, cannot be higher than 1, and same for the aggregation dynamics. But then if you go down, you can say if you have a group disaggregating of size 3, the most probable configuration is basically group of size 2 and 1, and then you can go down with all the sizes. And what you see here, and for the other data sets as well, is that this comes kind of gradually at the beginning, and then you go further away from your actual size. So this kind of suggests that there is a hierarchy in this agglomeration and disaggregation dynamics, so that you first acquire people one by one, and then you start acquiring chunks of groups. So it's neither a gradual nor like abrupt collision of medium-sized groups. It's something in between. And this is the same, it's symmetric. So it's the same for aggregation and disaggregation, and we didn't expect this to happen. I will go fast here. We just defined a dynamical model for groups with this in mind. The model is very simple. Basically, you have a group, you pick a node, and the node decides to leave the group or to stay in the current group. And if the node decides to leave, it has to decide to which group the node is going to. I'm going fast. Basically, we assume that the probability of leaving a group depends on the duration of the group, and this also depends on the size of the group. And this borrows from many interesting papers in sociology, where they found that the ability of a group to a level of cognition, I would say, sustain a group conversation, obviously goes down as the group increases, and you might observe this at a given dinner. As soon as the size of the table grows, at some point the conversation splits into 2. So it's natural to think that the probability of leaving a group decreases with the group size, and you can actually measure this in the data. So here we can measure the probability of leaving a group after tau time step decreases, and the factor here, 0.7, for example, if you instead study that factor as a function of the group size, you see that increases. So the survivorship increases with time and decreases with size. So we can put this into our model with a simple equation like this one, and we fit this with a logistic equation. And then for the group joining choice, we put the most standard notion in graphs, which is the fact that you have social memory. So you try to go back to the context you already met before. You can measure again this in the data. This is the fraction of known nodes whenever you have a group change against a randomized scenario. So as you see, you have memory in the system. So we put this into the model and pick the equations. And what you see, so here we're fitting the group size distribution and the node transition matrix, and we get back the other quantities as well. So we have a model that just, including the fact that people go back to the social contacts and the fact that you have a group survivorship that increases with size and decreases with time, you get back these quantities. And now it's quite of a nice and simple model to play with. It's fast to run compared to other models that take into account the full memory of the system given by all the tensors of the states of your system. Also recreates the patterns found in other cases, like people interacting in scientific conferences. And then if you want, you can play with this. There is the code online. So the next steps from my point of view would be to try to study the structures and the different structures and temporal paths generated by this evolving hypergraph framework. We also define temporal hypercores. This might be one thing to investigate. And obviously the other aspect would be now to put together what I presented at the beginning and at the end, which is how does the temporal component of the structure affects basically the dynamical process that you can put on top. Now, if you're interested in using some of these topics maybe for a different domain, you can have a look at the code that I used. So we developed a Python library, easy to install, which is called XGI, Complex Group Interaction, that contains a lot of methods and, most importantly, structures to handle group interactions. So you can have a look. There are also tutorials online and cookbooks, so it's easy to pick up, I hope. Unless, just let me know and I can help you help you with that. Very last thing, I just want to advertise this workshop that will take place in June, which is a workshop where you have tutors that are gathering together people working in groups of size, let's say 6, 7 people, and work for a week. In particular, the project lasts for 72 hours, and the goal is to have a report at the end of 72 hours. It's very nice. I participated both as a student and as a tutor, so I really encourage you to have a look at this. At the moment, there is out the call for tutors. So if you have a project that you think might be a nice trial for like a limited amount of time with a big group of people that are committed to get to see the end of it in 72 hours, this is a nice place to try it out. Unless from January on, there would be the call for student participation. This is it. Here there are some references, and if you have any question, I would be happy to answer. Thank you.